The relay, the electric bridge. Imagine you want to turn on a massive industrial motor using nothing but a tiny, fragile sensor. If you connect that sensor directly to the bulb, the sensor will literally melt. Can't handle the power. You need a middleman. That is where the relay comes in. At its heart, a relay is just an electrically operated switch. While a normal light switch requires your finger to flip it, a relay uses electricity to flip itself. Inside, we have an electromagnet. When a small current flows through this coil, it creates a magnetic field. That field pulls down this metal arm called the armature. When the armature moves, it forces two metal contacts to touch, completing a separate, much more powerful circuit. This is the isolation factor. The 5-volt circuit in my left hand is physically separated from the 120-volt circuit in my right. There is no electrical connection between them, only a magnetic one. That click? That's the sound of mechanical victory. You'll see 3 main pins on the switch side: common, normally open, and normally closed. Normally open means the circuit is broken until you power the coil. This is your standard on switch. Normally closed is the opposite. The circuit is on by default and turns off when you trigger the relay. Think of a fail-safe system or an alarm. Relays are everywhere. In your car, they allow a tiny ignition switch to engage the massive starter motor. In your furnace, they let a low-voltage thermostat kick on a high-voltage blower fan. And for high-speed applications where you don't want moving parts or that clicking sound, we use these. No magnets, just light-activated semiconductors. Whether it's protecting your delicate microcontrollers or controlling the power grid, the relay is the bridge that makes modern electronics possible.